Welcome to a new DoubleFox CorrMeas tutorial, the software for microscopy automation. I would like to show new features of the CorrMeas software, aiming in the direction of no code or low code. Any kind of automation commonly means one first has to program the automation. If the tasks to be accomplished are in some means predefined, the automation process can be simplified by having predefined procedures which can be combined in a certain manner. In CorrMeas, we have added now functionality to create automation for critical dimension measurements without writing any line of code. For this tutorial, we use a ZEISS field emission scanning electron microscope with a Gemini 1 column, together with the CorrMeas software. We see here a sample which we have also used in previous tutorials. We want to measure the width of a bar on this sample. It's a horizontal structure, and we can see it here. Let us activate the crosshair. So in this tutorial, we want to automatically measure the width of this conductor here. Yeah, so vertically. These structures are organized on the sample in a rectangular matter. So we have many different positions which have the same properties, and we want to go to all of them, capture an image of this structure, and measure the width of this bar. Yeah, this is the center of the area of interest. We go here, and let's then, okay, we stop the beam. Then we switch to the CorrMeas software. We want to create a point, which we will give the coordinates 0, 0, like that. This is our starting point, and it is here. And starting from that point, we want to create a grid that has positions horizontally separated by 1.6 millimeter and vertically separated by 2.4 millimeter. And let's say we put 10 in X direction and the distance 1600 micrometer, and let's take 4 in Y direction, separated by 2400 micrometers, or 2.4 millimeter. Negative sign, that means that we go downwards with the grid. Okay, when I press add, then it creates this. The next step is to align the grid to the real positions of the stage. We are here on the edge of the sample. Then let us go to the first area of interest, the thick one. Good. Let's focus a little bit like this. We center the structure and go to the CorrMeas. Then we select the upper right position and add it to the area of interest, to the base coordinate system. So let's go back to the SEM. Then we need to go 10 positions or 9 positions to the right. So we are on the first one, and then second, third, fourth, fifth, sixth, seventh, eighth, 9, 10th. Let's go down here. In the center. Focus. It's okay. We have some stigma, but shouldn't matter so much. Good. Let's go to the CorrMeas, and we now need to select the upper left corner. And if everything works, we have an aligned coordinate system. That would mean, let's go back to this one here. And you see, if we look in the live image, it's there and going there. We are here. Yeah. Now the others should work as well. Yeah, this is also there, and we should maybe have 3 points. That is the best coordinate system. So let's do the alignment here and the SEM side. This here and give it a focus. This is quite with stigma. We can just use some kind of autofocusing here. Let's do this. This is the image module from CorrMeas, which is running now, making a fast autofocus operation. You can see now it's going to the stigma, and after it has done the auto stick, it does another focusing step. Yeah, that's it. Now we have a stigma corrected image, and yeah, good. We add this again now to the list of points, and then we have aligned a coordinate system. The next step is to create the image acquisition. So we use the state system of CorrMeas. The state system records system states and also can store reference images. This, for example, we will use this state here, reference image, and you can see it stores a lot of parameters from the ZEISS electron microscopes. The state system is very flexible. It can be used for any microscopes because it works by scripts. And we will use this now in the imaging, which just takes an image with a predefined brightness contrast detector and magnification. So let's go to the SEM and find a clean area of interest. Maybe go to this one here. Yeah, let's take this. We take some zoom level and we center. We should go to the center. Like, well, we can go a little bit to the left. There's a lot of disturbances now here, but shouldn't matter so much. We take a zoomed out view, which is so large that the particles and so on doesn't disturb so much. Then let's switch to the CorrMeas. Beam shift is off. That is, yeah, and then we go record the reference imaging state, and we call it ref demo, like that. Now it's recording the image, storing this. Yeah. Okay, now we have that. Then we should choose an area of interest to image this. Maybe this here. I would like to use the SE detector for this because this is not so sensitive to charging and particles and so on. So we use this view and go to the CorrMeas and say, please record the image now, and we show, let's call it image demo. Okay. So let's try it again. We first want to activate state ref demo. Then let's see what it's doing. It's recording this and it should center the area of interest. Then we go back to the CorrMeas, say image demo, and now we have the area of interest there. Okay, that's good. Keep it like that. The next step is to define the image evaluation. We go to the image filter designer. This shows the current live image of the SEM, and we use this as a source. For the first test, we first now take a part of the image. Right now we have some dirt here, but like maybe take this area. Then we take the min-max average filter, which then can do a horizontal evaluation. We see we have several maxima here, so this data is a little bit noisy. We could add some filtering in here. So let's see. Yeah, now this looks much better. What this is doing, it integrates from left to right, and you can decide what things to take here, the S, and to measure the width. So we have the left bar here should be a maximum, the zero is maximum, and the right border should be a minimum, and -1 means the first from the right. And it should measure the width, which is actually 2.525 micrometer. Let us just check when we have the SEM running, we can activate this as a live image and see whether this will somehow stay the same. You can see here this how much variation we get just by let it scanning. We have scan speed now 3. We probably will record something with 6. Then let's go back to the thing here, and now you can see that it just varies by let's say 50 nanometer or so. So this precision is good enough. So we accept this, switch the live image off. Now we can choose what to do. This has generated some code now to evaluate this image. And we can from here now create a acquisition recipe, which also acquires the image. And I click this now. For acquisition recipe, we need to select the imaging steps that should be used before or called before grabbing the real image. So we have previously defined the ref demo and also the image demo. First, the ref demo should be activated, which then searches for the area of interest and centers it, and then the image switches to the imaging condition. So this should be good enough. And we press OK now. And it asks for a name, let's say acquisition capture demo, like that. Recipe added. Now we clear this again and close it. And we have now the capture demo recipe here. And if everything is working correctly, the only thing we need to do is mark all the points, add them to the list of images, and then start. And we can watch the SEM. It's recording the first image, centering area of interest, recording the second one, storing it, and you can see in CorrMeas it has also evaluated the image and measured some width here. Yeah. You can now watch how this is working. Now it is finished. You can see we have recorded all the images, and it has also calculated the width. So we can sort after width and then see This here is garbage. Some things didn't work, but for example, this one or this one here, this is that one there, and this one is actually the last one. So it seems so that the images on the bars on the right are not totally. It's a little bit distorted, but we have a variation from 2.3 to 1 nano. This is micrometer, 2.3 to 1, and the upper one is 2.19, and we can now try to measure this here in CorrMeas. So we have this here, and let's just measure it by hand, what it should have here. So this is 2.17 when I measure it by hand. It's a little bit, you see 1 pixel. One has to zoom quite far in. If you take the middle of this, we are at the 2.19. And when we go to the, let's say this, which maybe this bulb has changed something, but when we go to this one here, this should be wider. This is 2.28. And when we measure this like that, 2.26. Yeah, okay, so 9. Yeah, in that range. Yeah, you see the measurements correspond with the thing that this has evaluated automatically. Let's have a short look in this code it has generated here, because what we did is generating code. So we can see this. Let's close the other windows here. We can see this in the automator. This is the code it generated. We can view this in a visual representation. There it's maybe a little bit more. So the capturing loop here is the outside loop. Then it finds the position to go to, table move. And then here come the 2 states, ref demo and ref image demo, before acquiring the image. Then the table grabs actually the image. And then we have the things we selected in the filter. So first we fetch the image from the storage, then we crop it. It was the selected area. Then we filter it a little bit, and then we average the image to the right, find the corresponding minima, find the maxima. This is used with the function find min max, which is built in. Then it takes the correct maximum and minimum. This function finds more or less all maxima or all minima, and then it checks if arrow is okay, if there's no error. Error could be, for example, if there are no maxima found or something like that, then it would set error to 1. If this is not the case, it selects the right one. And then it checks furthermore whether right is smaller than left. And if yes, then it also sets the error. So the left bar should be smaller in the X scale than the right bar. And then in the last end, it plots the results that we have seen and delivers back the result, which is then stored in the column width. So that's the whole workflow in this program. So if, for example, if this wouldn't work so good and you wanted to insert another autofocus, for example, we can go do this here. To add that just before the grab here, just drag it here, image opt photos. That's it. And that's enough to set the autofocus. Now we can copy it back to the recipes, give it the same name. Praise. Okay, now it's active. We can close this, delete our measurements maybe, and press start again. When we switch to the SEM, it's recording the image, the first one, then zooming in, making the autofocus. That's it. Acquiring this. It only makes an autofocus, not autostigma, so that depends on how good this is. But for autostigma, one should not only have the horizontal lines, but also vertical ones. Okay. So you can see it now does an autofocus before each image acquisition. And that's what we wanted. Many thanks for your interest. You have seen for simple automation tasks like localizing an area of interest and performing a width measurement, no programming is required. And with a new code generation functionality, all steps can be interactively defined. For more information, visit the DoubleFox website.